Here's an experiment you can try in your own home. I have here a lid from my cardboard box. Inside that lid, I have taped down some aluminum foil, just so that it fits in the bottom there. And then, with some scrap foil, I'm going to take a square about an inch, about an inch by an inch. So about a 1 square inch piece of foil here. And I'm going to try and turn this into a ball, but I'm not going to wad it up really tightly. I'm going to try and keep it very, very light, and so that there's a bunch of air in the middle of it. So I'm just going to very gently kind of turn that into kind of a ball like this. It doesn't even have to be perfect. There can be big open spaces in it, and that's fine. We're then going to take that ball that I just made and place it inside the box lid. And then we're going to cover the whole thing with a piece of, I have a piece of acrylic I'm going to use. And you might have just seen that jump around a little bit. But you can use pretty much any plastic to do this. Acrylic works pretty well. And then I'm going to take a kitchen towel. And it can be just about any piece of cloth, really. It doesn't have to be anything special. I'm going to take a piece of this kitchen towel, and I'm just going to rub this kitchen towel over the top of this, and we'll see what happens. And you'll notice that this ball inside there dances around. And if I push it back to the middle here, once it's been rubbed, you'll see that's kind of crazy. Push it back to the middle there. Let's see if we can rub this a little bit more. And now you'll see it stuck to the top. Now here's a cool thing. If I take my finger
Well, aloha everyone. You've probably already guessed what we're going to be talking about today. Static electricity. Or maybe if we want to get a little bit more technical, we're going to call it electrostatics. Now the word electrostatics comes from two very important things. Electro here means having to do with the electron, or actually electrum from way back when, but that's a whole nother story. And then static here, this word static means not moving. So this is about electrical charges that are not moving. Okay, so electrostatics. What is that based on? Well, everybody remembers their chemistry. We remember in chemistry that there are some fundamental particles that we need to know about. One of them was called the electron. One of them was called the proton. And one of them was called the neutron. And these three fundamental particles, actually two of these three fundamental particles, are going to make up all of what we see in electrostatics at the macroscopic scale. They make up most of electrostatics. There's a few other charged particles out there that you get to, in upper college level. But for our purposes, normal matter, we're going to deal with protons and electrons. So, if you remember your chemistry, electrons are negatively charged. And protons are positively charged. Now, there's one thing that's very important, and it's a very common misconception that people have. Lots of people think both of these can move around. Well, in certain times, electrons are able to move back and forth between different objects. Why? They're on the outside of the atom. If you remember in chemistry, you probably drew something like this. You probably drew something like that. You put electrons around it, going around, right? And so you had something like that. Maybe they called those valence electrons or the valence shell or something like that. Maybe they talked to you about an electron cloud. But in any case, as these electrons go on, it's very easy to rip these off of here and send them somewhere else. Protons, on the other hand, are stuck here in the nucleus of the atom. And so because of that, it's very hard to make protons move around. In fact, it's very hard to liberate them from the nucleus at all. So because of that, the protons don't usually move, whereas the electrons move around quite a bit. So let's imagine we have two objects. So here are two generic objects. And they start off neutral. So if they're neutral, the number of protons has to equal the number of electrons. Both of them. Protons equals electrons. P plus for proton, E minus for electron. Now, if we take a whole bunch of electrons from one object and transfer them to the other object, we're going to end up with an object over here on the right that instead now has more electrons than protons. And so because of that, there's going to be more charge from the electrons than the protons can cancel. That means overall, this object is going to have a negative charge because it has too many electrons. Now over here on the left side, this object had the same number, but we took away some of the electrons. So now the number of protons is greater than the number of electrons in this object on the left. What does that mean? Well, that means that the protons now have more charge than the electrons can cancel, the ones that are left. And so because of that, this object is going to have a positive charge. It's not that we added any protons to this object. It's just that the electrons were removed, and there's an excess number of, there's the same number of protons, but there's a deficit of electrons to cancel that out.
But how is it we get electrons to move from one object to the other? Well, it really depends on the type of material. In some materials, like metal, they move back and forth quite readily. But in other materials, they have to be encouraged, and it's very hard to move those electrons around. That's the difference between a conductor and an insulator. So here, I have an insulating rod. This rod has been hung from a ring stand by a small piece of fishing line. And I have a second rod here made out of the same material. These are both nylon, I think. And we are going to take a piece of wool, and we're going to rub this wool on this rod. By rubbing the wool, we get static electricity, and if you listen carefully, you might be able to hear it. So, now that I have charged this rod, I'm going to do the same process to this rod. Only one end of it. I think I'm going to charge this side. And so I'll just very carefully hold that, and we will rub this wool against the nylon rod. That should probably be enough. And then I'll very carefully let go. Now, when I take these two rods and I bring them close together, watch what happens. One rod is putting a force on the other one, and they're able to push each other around. You'll notice also that I do that on the side that I charged, and it pushes it. However, if I try it on this side, pretty much nothing. Why is that? Well, because both of these have similar charges. Both of these, in fact, have a negative charge here. You don't need to remember negative or positive on what material combines with what. What you do need to remember is that these two have the same type of charge. And by doing this, they repel each other. So we have an interesting revelation here that like charges, if I push too hard, of course they touch and they go flying around, but we have an interesting revelation that like charges repel. I also have a third rod. This rod happens to be made out of glass. And I also have some silk here. Well, it's not actually silk, it feels like fake silk, because real silk would feel much nicer. But what I'm going to do is I'm going to take this silk and I'm going to rub it against the glass rod. in the same way that I use the wool against the nylon rods. Now, assuming that this still has a charge from when I rubbed it earlier, we might be able to see a little bit of an effect when I bring the glass rod close to the nylon rod. Let's see what happens. Well, that's different. That looks like the opposite of what was happening earlier. Instead of pushing the other rod away, now these two rods are attracted to each other. So because of that, we know that they don't have the same charge. We know that these two rods have opposite charges. And you can pull this rod back and forth using this one.
So there was a guy who did a lot of experimentation on this, with the idea that like charges are going to repel and opposite charges are going to attract. His name was Charles Augustin de Coulomb. And he came up with a relationship between the force that two objects exert on each other and the amount of charge that they have and the distance between them. So, the electrostatic force that is felt between any two charged objects is going to be equal to K Q1 Q2 over R squared. So, what's going on in this formula? Well, K is going to be what is called Coulomb's constant. And it has to do with how strong the electrostatic force is in our universe. In our universe, this happens to be approximately, K is approximately equal to, close enough for our purposes, 9 times 10 to the 9th Newton meters squared per Coulomb squared. These Q1 and Q2s over here, Q1 and Q2, they are the charges of the object. That's measured in coulombs. And R squared here, or, well, R here, is going to be the distance between the two charged particles. And obviously over here, Fe is electrostatic force. So you'll notice a couple things. If you increase the amount of charge on each of those, you're going to have a larger force. The other thing you can do is you can increase the radius, or you can decrease the radius. And you'll notice that the radius is inversely proportional to the force. So when radius goes up, well, not radius, when distance goes up, the force goes down. So the farther away you get, the less force you feel. Okay, but that having been said, what does that K mean? Well, K measures the strength of the electrostatic force in our universe. You might remember gravity from the previous class you took, and there was a law of universal gravitation that looked very similar to this. Do you remember Fg is equal to G, m1, m2 over r squared? That was the law of universal gravitation. And if you remember, this G, the universal gravitational constant, was 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, compare these two numbers for our constant, 9 times 10 to the 9th versus 6.67 times 10 to the negative 11. This is a tiny number. This is a humongous number. It turns out electrostatic force is much, much, much bigger than gravity ever will be. So let's take a look and see how we would apply Coulomb's law in a real-life situation. Let's imagine that we have two objects, one here, one here. Maybe they both have the same amount of positive charge on them. They don't tell us what the charge is, but they do tell us that they're equal. So they both have a charge of lowercase q. And maybe they're separated by a distance of 1 centimeter, which is 0.01 meters. And I want to know what is the charge that they would need to have in order to create a force. So they're pushing on each other, they're going to repel, and to create a mutual force of 1 Newton. Now that doesn't mean 1 Newton total between the two of them. That means the left one's pushing the right one with a force of 1 Newton. The right one is pushing the left one with a force of 1 Newton as well. So what is the force of 1 Newton? What kind of charge would we need in order to cause that force to arise? Well, we can use Coulomb's law for this. F equals K Q1 Q2 over R squared. We know that Q1 and Q2 are the same. They don't tell us what they are, but we do know that they're the same, and they're both equal to this lowercase q. So it's going to be K Q Q over R squared, which is the same as just saying K Q squared over R squared. Okay, let's solve this thing for Q is what we're looking for. So it's going to be F. We're going to move the R squared up, so times R squared, divided by, we're going to move Q squared down, no, we're going to move K down to the bottom. K is equal to Q would be squared, so to get rid of the squared, we take a square root. This is equal to the square root of, well, the force is 1 Newton, times R is 1 centimeter, so 0.01 meters squared, divided by K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, before you reach for your calculator, take a look at the units here. We have newtons here canceling newtons there. We have meters squared on top and meters squared on bottom. And we're left with a Coulomb squared on the bottom of the bottom. But we are still under the radical, so that's going to get square rooted. It's going to come up to the top as just coulombs. All right, so now we just need to crank some of the numbers really quickly. And I get 1.111, repeating, times 10 to the negative 12 coulombs. So 1.111 times 10 to the negative, that's kind of messy there. Let me see if I can write that better. 1.111 times 10 to the negative 12th coulombs. So that's electrostatic force in a nutshell. Mahalo for watching, and see you next time.